There's one more thing that we have to discuss about reservoir depletion. So we said that whenever there is reservoir depletion, basically pore pressure goes down with time. As pore pressure goes down with time, effective stress increase, and we saw the equations for that and how the Mohr circle looks like when you have depletion. It goes from, this one is before depletion, and this one is after depletion. So effective stress increase, both horizontal and effective, and together with that we have usually a decrease of porosity and an increase of effective stresses. For example, if you had a porous medium like a sandstone, where your permeability is mostly made out of pores, do you remember what is permeability proportional to in a porous medium with pore sizes of a given size? No? Well, I can tell you the answer for that. Permeability is proportional to the square of the pore size. This is what is called the Kosenik-Karman equation. So if your pore size decreases, your permeability is going to decrease with the square of that pore size. And when you have a fractured medium, I already have the fracture over here. Do you remember what is the equation for the permeability of a fractured medium? It's similar to this one, but in this case, permeability is proportional to the cube of the fracture. So if your fracture width changes a little bit, your permeability is going to change a lot. And basically this is what we want to calculate with depletion. There are several effects of depletion. Subsidence, sometimes full reactivation, but many times one of the biggest problems is the decrease of permeability. And the problem of that is that imagine that if before you had a production rate that without loss of permeability was very high at the beginning, and with a long tail, now if you have decreases of permeability with time because you have compaction, your new production rate probably is going to be as high as the beginning, but it's going to decrease much quicker with time. So this one would be with loss or reduction of permeability. Let me call it reduction. So from one point of view, this phenomenon of compaction is not good. It's not good because it reduces the permeability as a function of time. But there is one more thing, which is the one thing that we're missing, which is important to understand. There is going to be also a good side of compaction. Can you guess which one that is? Anyone? What? So
Water flow?
no. I mean, we're not doing any secondary recovery here, just primary recovery. So what we're saying is that many times when you deplete these reservoirs, compaction reduces porosity, closes fractures, and makes the production rate go down. But there is actually a good side of compaction. Yes?
Does it like push oil and gas out of pore space?
Exactly. And how is that called? That's one of the drives recovery, for primary recovery, right? And that's called compaction drive. And compaction drive is going to depend on what is called as pore compressibility. And that's the only thing that we're missing about this problem of reservoir depletion. So let me see, 83, 84. 86 over here. Let me write over here. So reservoir compressibility is defined, it's called CPP, and is defined as the change in pore volume due to a change in pore pressure, and that's exactly what we're doing in this case with depletion, divided the pore volume. This is a parameter that you use in reservoir engineering in order to quantify what is this compaction drive. So if there is a lot of compaction drive, you're going to recover much more hydrocarbons because of the compaction of the rock as you lower the pore pressure. And the good side of this is that it can help you recover more oil because of the compaction drive. Remember, this, if you're going to remember this, probably remember this like squeezing like sponge, right? The softer it is, the more you can squeeze it, and the more fluids you can get out of this. So how does this link now what we have been doing so far? Well, this CPP, it turns out to be the bulk rock compressibility divided the porosity. And the bulk rock compressibility is defined as the change in bulk volume divided the original bulk volume due to a change in pore pressure. But notice that this is not other thing but a volumetric strain. Change of bulk volume divided by bulk volume, that's just a volumetric strain. So this compressibility, it turns to be the change of volumetric strain due to a change in pore pressure. Let me put this one somewhere over here so I can write what I want to write next to this. And this is going to be equal, just wait a minute, Jeffrey, you can take a seat if you want. This is going to be equal to, according to the equations that we derived before, it's going to be equal to the change in volumetric strain. Remember that we just have one strain in this case, divided the change of pore pressure is just this. It's a BO coefficient divided the constraint modulus, where the constraint modulus can be calculated with this equation, constraint modulus M. So what I like that you do now is that you calculate this bulk compressibility, and after you get that bulk compressibility, you calculate the pore compressibility for the example that we were working on last week. So let me see, I can fit everything in here. So this is our example, right? I'd like that you tell me what is CVP and what is CPP. Let me put the equations over here. And you have already some of those parameters in there. you need the equation of M. Here it is. Let's see, Mr. Barmal, you don't have any points, class points. Do you think you can solve this problem? Yes or no? Or you want to give the opportunity to someone else? So as you wish. 2 minutes, you have to solve it in 2 minutes. What units? So that's a good question. Do it first in MPa, but eventually I want the answer in PSI. Okay. And it's going to be a number divided something in the order of a million PSI. So I'm gonna ask you to give me the answer in order of micro. 1 over PSI. So 10 to the minus 6, 1 over PSI. Okay? So let me help you a little bit here. So we said that CVP is going to be one small correction here. This is a positive amount, so this is going to be alpha 0.9 divided by m. Oh, we have there m. Here?
No, like, yeah, there.
Yes, you're correct. Yeah, it's 10 to the 9. So anyone has? Yeah.
Should you put a negative sign next to 0.9?
No. I just said that that this is a positive. Actually, in this definition, I believe there is a negative sign somewhere over here.
Okay.
But I'm pretty sure it's positive. Mr. Barmal, you have the answer for this.
Is it 6.08 times 10 to the power of negative 11?
Maybe, can you put it to the power of 9 or negative 9?
608 times 10 to the power of negative 9?
608. I'm not sure, okay, but we'll verify in a bit. And what about in terms of PSI? I have the answer in PSI. So remember, you have the conversion here, okay?
Is it 8,
Go ahead.
8.82 times 10 to the negative 9?
Say again?
8.82 times 10 to the negative 9?
No, that's not the answer I have.
Minus,
Negative 9.
is it 0.42 per microsip?
Go ahead.
Is it 8.82 to the power of negative 11?
No. Everyone has a different number.
For that part?
For this one or for the other one?
For that one.
Okay, let's do the following. It's as Miss Alada would say. It's 0.42 times 10 to the minus 6 over
Yeah.
1 over PSI.
That one is wrong.
This one is wrong?
It should be 0.068 times 10 to the negative 9.
Like that?
Yeah.
Point
Otherwise it would be to the negative 11.
0.06?
oh. Yeah.
Yeah.
Okay, and then what is going just let's work in PSI, because actually these compressibility values, they are mostly done in terms of PSI. What is going to be CPP then? Mr. Barmal, can you tell me the answer? Yeah. It's going to be about it's about 2, okay? 2. What are you doing with the light there, Mr. Boswell? Turning off and on.
Thinking too hard.
Yeah, thinking too hard. Okay. Well, I'm glad that this is making you think hard. Okay, so this is about 2.0 times 10 to the minus 6, 1 over PSI. That seems like a very odd unit, okay? So usually what is done in this case is all this thing is called a microsip. So you see it's more or less like PSI inversed. So 1 over PSI, so the inverse of PSI is called a sip. So it's a microsip. And this is the pore compressibility that in this case you will use for this rock. Something important to remember here is that the typical compressibilities for rocks vary more or less from 1 microsip. There are some that are even tighter than this, but more or less from 1 microsip to 20 microsip, where this is not very compliant. It's a very stiff rock, and this one is a soft rock. So if you have a lot of compressibility, you may expect to have quite a bit of compaction drive. Yes?
That's just like a ratio, right?
What do you mean a ratio?
Like compressibility. Like for it to make sense, you have to multiply it by the volume.
Times the pressure. So you see, you multiply this times the pressure, and it gives you a change of volume, a change of porosity actually. All right. So that was the only missing thing that we needed to finish this topic of depletion. So the decrease of pore pressure lowers the total horizontal stress, keeps the vertical stress constant, increases both effective stresses, and lowers porosity, closes fractures, and that lowers permeability. So this is the end of all the theoretical content. Let me stop this.